If I can borrow that please, KJ, thank you. Thank you. Okay, so what we're going to learn in this lesson is just a couple of techniques on how to integrate. So it's not, there's a little bit of stuff that's new, but for the beginning it will look familiar. So for example, let's start off with this as an example. I ask you to, let's say, integrate, I don't know, let's say something like sine x cos x. Now, you don't need any special integration by parts rule here. You don't need to use a substitution. You can do this little trick. Watch this. Now, who can spot what I have inside the integration now? Not quite, Sean. Yeah, well, in this case, sine 2x. You said cos 2x.
Oh.
Yeah. And that integrates quite nicely. That's just going to be a half minus cos 2x over 2 plus c. So you see, by using the trigonometry rule, we've simplified it a lot. Okay, but what about a little bit of a harder one now? Let's say you have something like integrate cos 2x sine 5x dx. Now, why can't I do the same trick I did before? What's stopping me? Yeah, the 2x and the 5x, yeah. So we have to use some kind of a plus b rule here, compound angle rule. Can I scroll down? Yeah. So, on the side here, I should note, let me think what will I need here. I'll need a 3x plus x. So I can say, and it's sine and cos, so I need sine. So sine 3x plus 2x is, no, that's not it. No, that's not it. Stop, that's not it. I need to make a sine 5x and a cos. Oh no, that's it, sorry. I apologize. No, that's not it.
No, it's 5. Oh, that's 5 minus...
Yeah, 5x plus 2x.
Yeah.
Because then I can get sine 5x cos 2x, sine 8, yeah, plus sine 2x cos 5x. And I can do the same thing with the minus. And I get sine 5x cos 2x minus sine 2x cos 5x. And then if I add these two lines together, here I get sine 7x plus sine 3x. That's equal to 2 cos 2x sine 5x. Because they add and these cancel. If I get rid of the 2 here, I can end up with this. But this is what I have in the question. Cos 2x sine 5x. So what I can do is change this into a half integrate sine 7x plus sine 3x dx. And now I'm finished because this just becomes a half minus cos 7x over 7 minus cos 3x over 3 plus c. Yeah.
Where does the 1 over 2 come from?
Well, it was originally 2 cos 2x sine 5x on the right.
What?
What? This and this will make...
Oh.
Yeah? Got that? Yeah? Is that okay? Can you see the idea? We're using trigonometry rules to simplify it. Okay, on to another example now, but of a different type. So you might remember, a little bit ago, we had this integration, 1 over x squared plus 1 dx. Does anyone remember that?
Tangent.
Nearly. Tan inverse x plus c. There is another one I want to do. Let's see how I'll do this one. This is... Let's see. Let's start off with saying y. So anyways, we know this one, so let's just get rid of that. Y equals sine inverse x. And I'll draw a triangle. And if this is x, and this is 1, because it's like that, then what's this side? 1 minus 1 minus x squared. Okay, I shall use implicit derivatives. So, before I do that, I'll just get the y, the sign over. Now, the implicit derivative, this becomes cos y dy dx, and this becomes 1. So that means that dy dx equals 1 over cos y. So that means y equals integrate 1 over cos y dx. So that means sine inverse x equals integrate 1 over cos y dx. And that means sine inverse x equals integrate, and what's 1 over cos y? Well, let's look at here. Cos y will be square root 1 minus x squared over 1. So cos y is just actually root 1 minus x squared. So we end up with this result, that if we integrate 1 over root 1 minus x squared, we'll get sine inverse. So this is another integration of a trigonometry, resulting in a trigonometry function. It's just like the tan inverse one, except it's with a root and with a minus, we'll make a sine inverse. Continue. Oh yeah, writing it down would be a good idea. Oh, and I should point out, and I'll say this, I know I said this, but I said it again. In the exam, there are proofs. Remember last time we did the trigonometry proofs? Just to be clear, if it has a sine, a cos, or a tan in it, they could ask you to prove it, which includes this. I've seen this proof asked on the exam twice. So if something has a sine, a cos, or a tan in it, they can ask you to prove it, including this. So this was on the exam, they asked you to prove this. That, to prove this, that if you integrate 1 over root 1 minus x squared, you get sine inverse x. So anything that has a sine or a cos or a tan in it is something that could be asked in the exam to be proven. Yeah. The last part here to here? Cos y? What's cos? Adjacent over hypotenuse. So cos y is just this. Agreed? Yeah, so cos y is just that. Yeah? Agree or disagree?
assume the triangle to be 1.
No, there's no assuming here, because y is sine inverse x. Or rather, you can say that this way, sine y is x. But of course, sine must be a fraction, so the fraction here is x over 1. And sine's definition, sine of angle y, is defined as the opposite of the hypotenuse. So this has to be the opposite. This has to be the hypotenuse, and the y has to be the angle. There's no assuming or choices here. Yeah or no? You're not happy.
So it's a ratio thing, right? I mean,
it's a ratio thing. If you want to be super technical, you can multiply all these by k, but in the end it will change the result. Yes?
That is cos y or cos inverse?
Where? Here?
Yeah.
Sorry, that's cos y, because it's derivative of sine y. Just like derivative of x is 1, I derivative differentiate here. This is okay, I'm not sure what's going on. You all look tired. Did anybody go to sleep after 3 a.m.?
no.
What time do you wake up at though? 4 a.m. WTF? What's up with that?
Well,
From 3 a.m. to 4 a.m. you slept?
no, I slept at 4.
And woke up at?
Go back at 4.
And you woke up at?
Woke up 9:58.
8:58? Or 9:58? Then you slept much more than me, because I slept at 3 and woke up at 7.
That's crazy.
Yeah, but why do you look more tired than me?
Yeah, but I also at 9:50.
Yeah.
And I just come here. I just woke up.
That's half an hour. Okay.
I mean, you have a time to brush your hair and...
Oh, yeah, okay, sure. Yeah.
I was in this building.
Oh, yeah, life is hard. Life is hard. Continuing, can I do an example of this now? So, let's say I have integrate 1 over root 16 minus x squared dx. Now there's a trick here, and if you think about the tan inverse lesson, you might actually remember what the trick is, and you might think to try the trick here. It needs a substitution, but the question is, what do we substitute? Oh, come on, you couldn't have forgotten. Remember the lesson on tan inverse? If this was 1 over 16 plus x squared?
This is what section first thing.
Yeah, that's not going to work in the exam.
I have forgotten that.
Yes, I can see that.
Second minus first.
16 minus
Divide by x squared divided by 16 divided by 1.
Let u equals 16 divided by 1? Not that. It's going to need at least an x in it. No. What?
Root 16 minus x.
That's what she says. No.
Is this
Oh!
No.
Root x squared divided by 16.
Correct.
Oh, really?
Root x squared divided by 16, which is x over 4, which is a quarter x.
That's shocking.
So du dx equals a quarter. So dx equals 4 du. So this is equal to square root 1 over square root 16 minus 16 u squared. I can get that from this line. Yeah, because x is 4u. So x squared is 16u squared. And then my dx becomes 4 du. Now this is nice because I can take the 16 out. And what's the square root of 16? 4. So what's nice is they all cancel. And I'm left with 1 over 1 minus u squared, which is integrating to sine inverse u. But sine inverse u is sine inverse x over 4. Just like the tan inverse example. What's wrong, Lee? What's wrong?
Nothing.
Could have fooled me.
I'm just confusing about the 16 below that.
What about it?
No, I figured that out.
Okay. Do you have breakfast?
Yeah.
Okay.
Great.
By the way, what the heck is that stuff there?
It's not mine. It's like a protein shake or something.
It's tea.
Okay.
Okay. Continue? Yeah? Okay. What about something like this? 300 plus 32x minus x squared.
That's the right.
No.
I feel like we've done this before. But we don't
Yeah, well, what should I do?
Oh, computing the...
There we go. So this is 1 over... Well, you know what? I'll do the complete the square just on the side here. So I have minus x squared plus 32x plus 300. So that would be minus bracket x squared minus 32x minus 300. Minus bracket x minus 16 squared. That's going to be 556. Is that right? What is minus 300 minus 256?
44. Oh, minus 300.
It is, yeah.
No, it's 556.
So that equals minus x minus 16 squared plus 556. So that's equal to 556 minus x minus 16 squared. So this is equal to integrate 1 over square root. Oh, what's the square root of 556, please?
2 square root 139.
Oh, it's an ugly number?
Yeah.
2 square root
139.
139.
199.
I'm sorry, say again?
139.
139. Bracket squared minus x minus 16 squared. So this is where we use our trick. Let u equal to x minus 16 over 2 root 139. Or in other words, the square root of this over this.
139.
Oh my goodness! Thank you. Yeah? Yeah, we can go do this. Well, I mean, what we can do is we can get the du dx, we can put the dx in here, we can replace the x here with the u, we can simplify it, but we kind of know what the story is here. It's going to end up being sine inverse u. Because the whole point of using this exact substitution is to simplify this into a sine inverse u. Like if you look at the last one, the whole point of using this was to make these the same, and they will cancel with this on the top, because the reason this was here, it came from here. And the reason the 16s are here, it came from here as well. There wasn't a 4 to begin with. Just like with this one, there's a 1 here to begin with. So a number will appear here, and the number that appears there is because of this substitution. And likewise, this will have a common number that can be taken out, and the number that will appear there will cancel what appears on the top. In other words, I would be very surprised if I didn't get this. But you can check it yourself. I might be wrong. There might be a number at the front. Let's check it just to be safe, actually. I shouldn't be so cocky. No, actually, now I'm not sure anymore. Let's check to be sure. Okay, so what is du dx here? So du dx will equal 1 over 2 root 139 x. So that means dx equals 2 root 139 du. So this is equal to 2 root 139 du over square root 2 root 139 squared minus, now what is x minus 16? Here I said so look, x minus 16, what's that equal to? U times that. So this will be 2 root 139 u. Yes, as predicted, you can take this out, and because it's squared and square rooted, you're left with this, which will cancel that. So, yep, as I thought, they do all cancel, and you are left with sine inverse u when you integrate. So that's sine inverse x minus 16 over 2 root 139 plus c. Okay, write that one down, please.
So where
Yeah.
x comes from, du dx equals 1 over 2 root 139 x.
Oh, yeah. Sorry, that was from the substitution. So really, that should be beside that guy. And this is completing the square, so that's like in its own little box.
Du x and that.
Huh? How did I get this?
And x.
This x? It's from here. Yeah? No? Continue?
Teacher,
Yes.
how do you get sine inverse?
Huh?
How do you get sine inverse?
Okay. Because this is equal to this, which is everything we've done today. That's the form, when you integrate that, you get sine inverse u. Do you remember, Lee, the proof? Proof I did up here? Okay, great.
Teacher, I'm curious with the previous question.
Yes.
The one with 16.
Yeah.
Cancel out the 16 left with 4, right?
No, I cancelled the 16 with the 4 because the 16 is in the square root. What's square root of 16?
4.
Yeah.
And then.
Cancels the 4 on the top.
Oh, okay.
Yeah. Yes. Yes.
But how can you cross them again?
OMG!
And it's 2 square root 139.
Watch. 16 minus 16x squared, for example. Yeah? That's equal to square root 16 1 minus x squared. Agreed? which is equal to square root 16 square root 1 minus x squared, which is equal to 4 root minus 1 minus x squared. So if you have a 4 on the top, you can basically cancel the 4 with the 16s there. That's some good maths.
What about this case? 2 square root 139.
It's the same thing. Because this is 2 root 139 squared, and this is 2 root 139 squared. So this is like 4 squared and 4 squared. So my point is, if you had something like this, hang on, a over root a squared minus a squared b, you're allowed to quickly cancel the a with those two a squareds that are inside the square root. Now, can I continue? Alright. Now on to the hard one for today. This is the hardest one today. And it's the hardest one because it looks so easy. See, math is tricky like that. Right, so, what do we do? It seems like maybe we should just go straight into using our trick of saying u equals square root x squared over 16, or square root 16 over x squared. But no, it doesn't work. Yep. This is not cos, yeah. It's not sine and it's not tan because it's not 1 over.
Bracket 1 over 2, and then 2 something 1 over 2, something like that.
Nice try, nice try. Let me show you what to do. We start by drawing a triangle to help us. And we call this side x, and we call this side 4. And this side here would be square root 16 minus x squared. And we call this angle here theta. So basically what we say is, we say let, let me just write this over here, sine theta, no, wrong, let cos theta equals square root 16 minus x squared over 4.
Yeah.
So in other words, 4 cos theta will equal that. Okay, that kind of looks, yeah, that kind of looks helpful, because if I put a 4 here and a quarter here, then I can change this into a quarter integrate. No, oh, sorry, I didn't even need to do that thing with the, sorry. Integrate 4 cos theta.
Yeah.
But the problem is that's a dx and not a d theta. So, okay, let's get the dx into a d theta. But if you look at this, that's a bit of a pain, because differentiating cos is easy. What do we get when we differentiate cos? We get sine, that's fine. But differentiating square root is kind of messy. But we need to remember, if 4 cos theta equals that, then sine theta equals x over 4. Or in other words, x equals 4 sine theta. And this is much nicer, because now I can say dx d theta, what will that equal? 4 cos theta, yeah. So now we get dx equals 4 cos theta. So that's wonderful. So now we can go back to this and we get 4 cos theta, 4 cos theta, d theta. So we've changed our problem into this. 16 integrate cos squared theta, d theta. Okay, I'll pause for a minute, let you write that down. There's more to come.
16 turns to 4 squares, and then 4 minus x bracket 4 plus x, and then using the plus x.
Don't know if that would work. I don't know if that would work, because the answer is going to get quite complicated now, and I can't see how that would get to the answer, so I don't know.
Related to cost.
Yeah, it doesn't look like it at all. Continue. So we need to do something about the cos squared theta. So, on the side here, just for a moment, remember cos squared theta equals cos theta, no, what am I saying, sorry. Remember we have cos 2 theta equals cos squared theta minus sine squared theta. But also remember we have 1 equals cos squared theta plus sine squared theta. Remember that? Theta. So, if I add these together, I can get this formula. Cos 2 theta plus 1 equals 2 cos squared theta. So, therefore, cos squared theta equals 1 plus cos 2 theta over 2. And in fact, this is in the formula book, but it's in the formula book this way. It's in the formula book as cos 2 theta equals 2 cos squared theta minus 1 in the formula book. I think anyways. It's as a double angle rule. Okay. Can I go back to the question? No. Congested or stiff?
Yeah.
Sure.
Yeah, the maths will do that to you. Yeah.
How do you know is 1 equal cos square theta plus sine square theta?
How do I know that?
Yeah, I mean, I know the equation, but how do you know you have to put this together?
This isn't the only way to do this. Basically, my goal is to get a formula for cos squared theta. So you could have done it by changing cos squared theta into cos theta and using the compound angle trick. You could have done this by using other trigonometry rules. In other words, there's about, I think, 3 different ways to do this. And in fact, you don't even have to do it any of these ways, because in the formula book it gives you this rule, which you can easily rearrange back into this rule. So you have a few. My goal is to get a formula for cos squared theta. So I have a couple of ways to do it. This is just the easiest way, or rather, I should say, this is the way my brain thought of first. Continue. So, that cos squared can be changed into, we said, 1 plus cos 2 theta over 2 d theta. So that's wonderful, because that can be changed into 8, yeah.
1 plus.
And that's wonderful, because that can be changed into this. Theta plus sine 2 theta over 2 plus c. And you might be thinking, happy days, finished, because I have my answer. But there's a small problem. What's the small problem? It's theta. And theta wasn't the original. The original was x. So I'm going to need to change this back into x. And the easiest way to do that, what I'll do is I'll put this as 2 over 2, okay? So I can write it like this. You see what I did? So I'll just put it like that. And the reason for doing that is so I can cancel that with that to make it 4. And then multiply the 4 in. So that's 8 theta. What am I doing? I could have just multiplied the 8 in to begin with. It's sorry, multiplying the 8 in, I get 8 theta, 4 sine 2 theta plus c. Okay? And that's equal to 8 theta plus 8 sine theta cos theta plus c. Now what rule did I use there? How did I go from here to here? Yeah, I said sine 2 theta is 2 sine theta cos theta. That's why the 4 became an 8. Now why am I doing that? Because if I think back to my triangle at the very start, I said the relationship I'm making for theta is that the theta is the angle in a triangle whose side is x and 4 and root 16 minus x squared. So in this triangle, what's theta? Well, you could say theta is sine inverse
x over 4.
Yeah. And here, what's sine theta? Sine theta is x over 4. And what's cos theta? Root 16 minus x squared over 4 plus c. 4 goes into 8 twice, and so I'm left with now as my answer, woohoo, big fraction. On the bottom is a 4. It is not, that's a lie.
No.
It's a lie. Well, that's a dirty lie. That's a dirty, dirty lie. On the bottom, I can still cancel. 2 goes into 2 once, and 2 goes into 4 twice. Okay. 2 c. Alright, that's a 16 sine inverse x over 4 plus x. Thank you, Sean. X root x. Whew. That's the answer. Where did it even start? All the way up there. So it's hard. And it's funny because it's hard, and yet the question at the beginning looks so easy. Looks so easy, and yet it's so hard. The only good news, and it's not much, I can tell you that, but the only good news is in the exam, they usually tell you this in the question. As if that makes it much easier. In the question they usually say, let x equal 4 sine theta. So at least they tell you that, but you still have to do all this work. I know it sucks, but you know, it's the last lesson in this chapter. Oh, yeah.
Why not we don't put the theta into the sine theta?
Oh no, that's ugly. It's ugly because it will make this. You'll get sine 2 sine inverse x over 4. Which is ugly.
But it's not equal.
Don't say it, Sean. Don't. No, the 2 does not come out here, and the 2 does not go in there.
Okay.
Did you write this down? I don't know why you're tired. I did all the work. Right, so the good news is that's the end of the trigonometry chapter. So we have 2 big chapters left. Vectors, which is, I don't know, must be about 10 or 12 lessons, and statistics, which must be about 12 lessons as well. So what I want you to do is I want you to try these for a few minutes, and then we'll start on vectors. And the next lesson is so easy. Even a baby could do it. So you should be fine. It's mostly just drawing pictures of arrows. Okay, but don't be long. Don't fall.